Hi, my name is Eleni Tsitinidi, and I'm a senior at Davidson College. Today, I am presenting my research done in collaboration with Davidson College, Old Dominion University, and Jefferson Lab. My research focuses on using machine learning techniques to interface between experimental cross-sections in QCD theory parameters. QCD stands for quantum chromodynamics, which is a branch of nuclear physics that pertains to quark-gluon interactions. Specifically, we study the inner structure of the proton. This research is based on QCD analysis, and we map experimental high-energy scattering cross-sections to quantum probability distribution functions. As we can see in this graphic, we have an inverse problem. In the theory center of Jefferson Lab, the theorists have models that go from parameter space to observable space, and that is a one-to-one correlation. Our research focuses on going the opposite route, so going from the experimental cross-sections of observable space to parameter space, using a neural network. This is called an inverse problem because the set of parameters is not unique, so the solution space can have multiple solutions, a set of multiple solutions. Our research focuses on cross-sectional data that correspond to a range of 2 to 25 parameters. In addition, the cross-sections we train on are drawn from a hyperbox around a true experimental cross-section. We can vary the size and shape of this hyperbox to test the limits of our models. Lastly, we verify our results by comparing up and down quark parton distribution functions, otherwise called as PDFs, to the theoretical predictions. Let's now move on to the model architectures we've explored to tackle this problem. First, we have an autoencoder, the structure of which can be seen here. The autoencoder provides a robust dimensionality reduction method, and in addition, it has a high accuracy result. However, there is a limitation in that it does not provide multiple solutions. We have tested our limitations of our autoencoder model in improving in hyperbox as well as parameter space. We have increased our parameter reach as well as our hyperbox training up to 75% of the total hyperbox given to us by Jefferson Lab and up to 20 parameters of the 25 total. In that search, we have achieved a chi-squared metric of 1.49. That is successful because it is comparable to the theoretical parameters that theorists at Jefferson Lab already use, and as a result, our methods are comparable and more efficient than the methods that are already being used. On the left, you can see our PDFs, so our plots of parton distribution functions for 4 different distributions. We can see that our predictions are within 1 standard deviation of the true theoretical parton distribution functions. Moving on, we use a mixture density network. A mixture density network is a specific network that instead of outputting one solution for a cross-section, outputs the whole solution space. So what it outputs is a mixture of Gaussians, as can be seen here, which is a set of pi, mu, and sigma squared coefficients that describe the probability distribution of the potential solutions in parameter space. We can then sample those Gaussians, so for example, those 3 Gaussians here, and get 3 different solutions with their respective probability of existing. The following figure represents the performance of this model when predicting deep inelastic scattering data. On the left, you see our predictions made by the mixture density network, and on the right, you see the theoretical predictions used by using regression models at Jefferson Lab theory. We see that while they don't correspond one-to-one to each other, we still have the advantage of the multiple solutions, and we follow the distributions as they should be predicted. That makes our MDN a successful and valid model for the multiple solutions. In order to combine high accuracy and multiple solutions, we then come up with our third model, which is the AE-MDN. In the AE-MDN, the latent space of the autoencoder now becomes an MDN latent. This combination allows us to have a high accuracy solution, but also provide multiple solution space. This model is the model we will be using to go on forward and to achieve a chi-squared of 1.49 for the full hyperbox and full parameter space. This research should also note that it has been used to create a web app femto analyzer. This webhook femtoanalyzer is a tool that makes predictions using the trained models that we have described above. In this way, researchers can modify input data and observe changes in predictions, and so they can figure out the types of experiments they want to hold or what kind of theoretical parameters different cross-sections could hold. Thank you for listening to my talk, and this work was partly funded by the Center for Nuclear Femtography.